Okay, so I did mention that we need to be flexible with variables, all right, because even though a lot of times we'll use f of x or y of x or y equals f of x, that's not always what's being used in a specific function. And in fact, if you're applying this to some other field, it's likely that you're not going to be using x and y in f. You might be describing temperature, capital T, or time, little t, or pressure, P, or profit, P, or anything. So we need to be flexible with the variables. For the ease of the look of it, yes, we'll use x and y a lot, and f of x a lot, but realize that they just are representative, and we can use any variable we want. So let's say we had a function r of s. If we were talking about the derivative, what are ways that we would show that? Well, we could just say r prime of s, or we might say something like dr ds. And what you're seeing is that the notation is attempting to show us what is the independent variable, s in this case. So in the Newton notation, in the prime notation, where really the prime is telling us it's the derivative, and because we only have a function of one variable, s, it's understood that it's the derivative with respect to the variable s. The Leibniz is a little more, shows that a little more clearly, because it's saying the derivative of r with respect to s. So that's where the ds is showing basically with respect to s. All right, so now maybe we have z of theta. We use theta a lot for angles and trig. So z of theta, we might say z prime of theta as the derivative, or dz d theta, something like that. So let's look at a problem. Let's do a derivative again, but in different variables to see that it really is the same thing. We just have to be good about being flexible with variables. Okay, so we're going to here find dr d theta for the function r of theta equals 3 over theta. Then we're going to find dr d theta at theta equals 1. And notice the notation. So basically, this is saying find the derivative dr d theta and then evaluate it at the specific value of theta equals 1. So we'll do that. All right, so dr d theta, well, again, we could think of it as r prime of theta. It's still going to be the limit as h approaches 0. So it's now r of theta plus h minus r of theta over h. Because instead of thinking about f of x, we're thinking about r of theta. Okay, so now let's apply this specific function 3 over theta. Limit h approaches 0, r of theta plus h. Well, r of theta is 3 over theta. So r of theta plus h should be 3 over theta plus h. I don't really need brackets here. Minus r of theta, which is just 3 over theta, all over h. All right, and there we have it. There we have the limit that we actually have to calculate. Notice again, it is starting as 0 over 0. So we have to work our way out of it. We saw limits like this when we were doing it earlier. We need to get some sort of common denominator and work this out. So as a little bit of a shortcut here, what I could do is actually just multiply the numerator and denominator by theta times theta plus h, which would be the common denominator. And this will be a little faster for me than actually getting the numerator into that form. So that will become the limit as h approaches 0. So when I multiply this times theta plus h, theta plus h cancels, and I get 3 theta minus, when I do 3 over theta times this, the theta cancels. So I would get minus 3 theta plus h over, and then I have basically h theta plus h being multiplied in the denominator. So that made it a little faster than actually go ahead and getting the individual common denominators on top, which would be perfectly fine if you want to do that. I was just showing you an alternate way here. Okay, keep working. So this is 3 theta minus 3 theta minus 3h all over h times theta plus h. Okay, keep going. 3 theta minus 3 theta, 0. So I get minus 3h over h times theta plus h. And notice what has happened. The h that was causing the 0 over 0 cancels out like before. And then we get the limit as h approaches 0 of minus 3 over theta times theta plus h. And indeed, if we go ahead, oops, I don't need the limit anymore because I'm going to evaluate it, put in 0 for h, I get minus 3 over theta times theta, or in other words, I get minus 3 over theta squared. So what we found, dr d theta, was equal to minus 3 over theta squared. And now that wasn't the end of the problem. That was the first thing I was supposed to find. And then I'm supposed to do it for theta equals 1. So dr d theta for theta equals 1 would just be negative 3 over 1 squared, or negative 3. So dr d theta for theta equals 1 is negative 3. So that's the specific value of the derivative when theta is 1. And this is the general derivative, and this was the specific value. Okay, now I should mention there is an alternate form of the derivative, and going back to original f of x. All right, so you can write the derivative as f prime of x is the limit as z approaches x of f of z minus f of x over z minus x. This is not really a different form. It just happens to be nice for certain circumstances. We don't need to use it. But if you think just z as x plus h, then what you really have is z is x plus h. So x plus h goes to x of f of x plus h minus f of x over x plus h minus x. And notice, what is equivalent to x plus h going to x? That would be h going to 0. And f of x plus, oh, I don't like how that came out. F of x plus h minus f of x, and the denominator becomes h. So it is equivalent, perfectly equivalent. You would just find that there are some places that it might be just a little simpler to look at a derivative in using this form of the derivative instead.